Well, welcome to second semester organic chemistry. We're going to start with chapter 12, which deals with infrared spectroscopy and mass spectrometry. So I'm going to take a little bit of a different approach to organic, at least for the first few chapters. And we're going to talk about these techniques, lab techniques, which are instruments where we put the sample in and we get a lot of information by scanning it, and I'll talk more about it as we go along. And it's going to be a little interesting because we'll talk about it in lecture about the techniques, and then we're going to actually use it and solve some problems with these techniques once we learn them all in the lab. So anyway, you see a link here for a good website for IR spectroscopy. I also have that link posted in Canvas. All right, so just a little bit of a review from general chemistry. If you remember, the electromagnetic spectrum is just all the forms of energy that display wave properties. And so we can have, so all light travels at the same velocity, the same speed, but they differ in wavelength and frequency. You might remember that wavelength and frequency are inversely related. The longer the wave, the lower the frequency. So the bigger the wave, the lower the frequency. These divisions are somewhat arbitrary, and it'll be, so the edges might be a little bit different. But anyway, what we're going to do is we're going to focus on a couple of different particular electromagnetic spectrum areas. Okay, so here is just to remind you of what the electromagnetic spectrum is. We start all the way on one end with gamma rays. Gamma rays tend to have the smallest wavelength, a picometer, which is 10 to the minus 12 meters, going all the way up to wavelengths of actually tens of they could be in the meters, 1 meter, 5 meters, 10 meters. And then frequency is inversely related. So the lower the frequency, the longer the wavelength. And then over here, gamma rays have the highest frequency. And also, just to go along with it, is energy. So as frequency increases, so does energy. So we know gamma rays have the highest amount of energy. X-rays are very high energy. Ultraviolet rays, just above visible, have the little bit more energy, and that's what causes a lot of the sunburns and things like that. Then on the other side, so then we have visible, which I'll talk about in a minute, and then on the other side we have infrared, which is a little bit lower energy, longer wavelength, microwaves, even lower energy, radar waves, and then our TV waves and things. And then we know visible is a very small part of the spectrum, but if we spread it out, we can see that the highest energy visible light is ultraviolet, or right at the edge of ultraviolet, so very violet. And then our lowest energy or longest wavelength is the red, so almost getting into infrared. So, and then there's our spectrum. All right, and just a few other reminders or definitions. So what is spectroscopy? Spectroscopy, it's a technique where we measure the amount of radiation a substance absorbs at various wavelengths. So what's happening is you put the substance, you hit it with the radiation. If it absorbs it, then when it comes out the other end, the radiation will have decreased in amount, and that's something we measure. If it comes straight through at the same, like if the amount you put in comes out on the other side, then none of it's been absorbed. So it has to do with absorption of energy of a particular wavelength, which is, and that's why there's different spectroscopies, because as you'll see in this one, we're talking about infrared spectroscopy, IR, and so we'll be using light in the infrared area of the spectrum. There's also, in a couple of chapters, we'll be talking about ultraviolet, and there's often ultraviolet and visible go together, and so that's another type of spectroscopy. Anyway, this equation right here shows us how energy and frequency are related. So we said they're directly related. So as frequency increases, energy increases, and the frequency, let's see, the constant is called Planck's constant, and it's 6.22 times 10 to the negative 34th joules times second. So what happens is, since frequency is in per seconds, and the per second, the seconds will cancel, and then we'll end up with energy in joules. You're not going to have to do any of these calculations. That was just a reminder from general chemistry. Remember also that energy is related to wavelength. Well, actually, wavelength and frequency are inversely related, and so this is the equation. Sometimes you'll see it as speed of light is equal to lambda nu, or wavelength times frequency. So this indirect relationship, or you can rearrange this equation and find out that frequency is the speed of light divided by the wavelength, and so they're inversely related. C is the speed of light, which is 3 times 10 to the 8th meters per second, just in case you didn't remember that. And so wavelength has to be converted to meters before you can find the correct frequency. And then if you put these two equations together, you can find that energy is indirectly related to wavelength. Again, you're not going to have to be doing any of these kinds of calculations, just reminding you what some of the relationships are. Okay, so right now we're going to be looking specifically at the infrared region of the spectrum. And so what compounds absorb energy that is directed at the compounds that are in the infrared region of the spectrum, so that have energies that are in the infrared region. So again, you can go back to the spectrum, and you can see that that the IR region has wavelengths from 2.5 to 25 micrometers, which is the same as around 2,500 to 25,000 nanometers. A lot of times we'll use, instead of the wavelength, we'll use something called the wave number. That's probably what you want to be more familiar with. The wave number is really the number of waves in 1 centimeter, or another way to figure out the wave number is to take this, convert it to centimeters. So let's say 2.5 micrometers will convert to 2.5. If you want to convert this to centimeters, it's 2.5 times 10 to the minus 4th centimeters. And then if you take 1 divided by that, you'll get 4,000 inverse centimeters, or 4,000. Another way we say that is 4,000 wave numbers. So if you take the wavelength, convert it to centimeters, and take 1 over that, then you'll get the wave number. And that's mostly what we use, but that's how they're related. So usually we'll see the scale going from 4,000 down to 400 wave numbers. One thing that you'll want to keep in mind is that infrared spectroscopy is especially good at helping us identify functional groups. So it's a really good method for functional groups, as we'll see in the rest of this lecture, how you can identify different functional groups. They absorb energy of different amounts depending on the type of bond that we're looking at. For example, a CO bond or an OH bond, they will absorb in a very particular region of the spectrum, and then we can identify them. Okay, so one thing to also remember about infrared spectroscopy is that what it's measuring, or what's happening, is when you hit a molecule with infrared light, what it usually does, and if it absorbs that light, what it does is it will stretch its bond. The bond will be stretching. So what this picture is showing here is that bond lengths are not fixed, and so a lot of times if this happens to be a molecule here, they're going to be kind of bouncing back and forth. And so we often talk about an average bond length, what a particular molecule, a carbon-carbon bond, has a particular bond length. But generally speaking, they're kind of bouncing sort of like a spring back and forth. And so they might get a little bit closer. This is showing the internuclear distance. So if they get a little bit smaller, a little bit closer together, and they could stretch a little bit, and usually they stay in this region and they'll get smaller and bigger and smaller, and kind of like a spring bouncing back and forth. At some point, what this is showing is that at some point they can get too far apart and the bond will actually break, and so that's a bond dissociation threshold. But basically what we're looking at is stretches in bonds. And so that's a lot of what we're going to be looking at in the infrared spectrum. So this is a really good video. If you go to, I have the PowerPoint posted on Canvas where you could go to this link, or I've also linked it to Canvas, and I'm hoping that it'll work. It's got some kind of weird firewall kind of thing that sometimes it doesn't work for me. So hopefully it will work for you. If not, let me know and we can try to figure out how to see this video. It's just like a little short, maybe 5-minute video that kind of is going to be saying a lot of what I'm saying here. So you may or may not want to watch it, but it's a little bit more visual. And also just if you click on it, it'll take you, it's like a 20-minute video and it's done in segments. And so you want to click on the third segment to just jump up to spectroscopy, infrared spectroscopy. All right, so here's what I was saying. So a lot of times what we're going to be looking at is these vibrations, bond vibrations, and the ones that especially occur in the infrared region are called stretching or bending. And so these little while you're watching that, you can see that these are stretching, and we have symmetrical stretching or asymmetrical stretching. And sometimes if we're live in class, I demonstrate these, but you can see sort of like cheerleaders here almost. And then we have our bending vibration. So either rocking or scissoring in the same plane, or these are wagging in and out of the plane. So we have bending. Basically, we're going to be looking for bending and stretching vibrations. And I think I'm going to put the link to this page where I got these pictures from also on Canvas. Okay, so this is kind of the basic setup of any kind of spectroscopy, actually. So just depending on what the source is. So in this case, this would be an infrared source. Basically, it's shone into the sample, so a container that has the sample of question, and then if the light is absorbed, then when it comes out the other end, it will be lower in amount, intensity, or how much of the IR. So if it's not absorbed, it'll come straight through and you'll get the same amount of energy in the detector as what started with. But if the sample absorbs the energy, then what comes out the other end will be lower, and so then it's detected how much of it was absorbed. You can also think, as you'll see in a second, absorption and transmission are two things. So if you think of it as absorbance, how much is absorbed, so this side will be less. You can also think of it as how much of this light gets transmitted through, and those are opposite things. So if a lot gets transmitted through, that means not very much was absorbed. If a lot was absorbed, then not much gets transmitted through. So we'll see that on the second slide. So then it's detected, and there's some kind of output where it's recorded, and you can get a computer readout or a picture, which we'll look at in a second. An actual setup of a spectrometer, and this is not an analytical class, so you don't really need to learn much about it, but there's other things, like sometimes what you have to do is you have to zero it out, so you might need to have some kind of reference. That's the word I'm trying to think of. You might need some kind of reference to standardize everything, and then the sample. Sometimes you'll see a dual beam where it goes through a reference and it also goes through the sample, and then they're compared to each other. So there's lots of different setups. But the basic thing you just need to know here is the source goes in. If the sample absorbs it, then less will come out on the other end. Okay, so and this is what a typical IR spectrum is look like. And so actually, even though we talked about how much is being absorbed, like I said in the last slide, we actually are looking at percent transmittance. And so, as I said earlier, it's kind of the opposite of absorption. So if it absorbs, since absorption is kind of coming down this way. So right here, this means that a lot, at this wavelength, a lot was absorbed, or very little was transmitted. And so 100% transmittance would be up here, and that would be meaning that nothing was absorbed. So something here, so at these wavelengths or wave numbers, there's no transmittance, which means, there's 100% transmittance, which means there's no absorption. As you come down a peak, you have high absorption, very low transmittance. So 0% transmittance would be like nearly 100% absorbed. And so that's how you read it. So the lower the peak here, the more absorption there is. So there's very little absorbed in this region, and a lot here. So these are, but we call them transmittance peaks. So very low transmittance, but you can think of it as opposite. So it's a lot absorbed or very little transmitted. And so usually you'll see this percent transmittance, and here's wave number. And so, you know, that the previous slide didn't have very much, but you're going to scan through all these wave numbers. And so there's something that will be, you know, shifting the actual wavelength or the wave number. So it'll scan through all of these possibilities within the infrared spectrum. And so this is what a typical IR spectrum would look like. All right, so one thing that will be really helpful for you to remember is that you can divide an IR spectrum into different regions, and they have different kinds of absorptions associated with them. One thing that's not really on here, we have up here we tend to have our stretches, and down here we tend to have our bending. We'll talk about that more. But another thing to notice is that as you go from single bonds, so these are single bonds down here, to double bonds in the middle here to triple bonds, we tend to be at higher and higher wave numbers. That's a higher frequency, and that's because you show lower wavelength, higher frequency. That's because these bonds are a little bit stronger, and so when they do vibrate, they tend to vibrate at a higher frequency. And then we have our single bonds up here to an H. So these are all of our H bonds, OH, NH, CH, 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 and they tend to be very high frequency because the hydrogen is so light. And so you can see that there's different regions here. So right above 3000 tends to be the OH and NH, and we'll talk more about that in a little while. Also just above 3000 are our sp2 hybridized carbon hydrogen bonds, or our sp hydrogen carbon bonds, because again, the tighter this carbon is held, the higher the frequency of this bond stretch. And so this CH double bond will be a little bit lower, a CH triple bond will be a little bit higher. Then we have our single CH bonds. And then over here, now we're talking about our C triple bonds are in this region around 2200, and our double bonds are in this region, and then our single bonds are down here. So here's what I just started to say. So the alcohol stretches are particularly prominent. They will be something to really look for. They're going to be broad, and they're going to be strong, meaning they're going to come really far down on the on the spectrum, and they tend to be, like I said earlier, a little bit above 3,000, 3,400, 3,600 to 3,400 wave numbers. Amines also tend to be in the same region, but they tend to be sharper and less intense. Carbonyl groups are very, very easy to identify. They have a very sharp, strong peak around somewhere between 1,800 and 1,650 in inverse centimeters or wave numbers. And then, like I was just saying a minute ago, the CH stretching can vary a little bit because of the hybridization of the carbon. So if it's a single bonded carbon to an H, it absorbs just below 3,000. If it's an sp2 carbon, that means that this carbon's held a little bit tighter. And so this bond is going to stretch a little bit more and not have quite as much energy. Or it is going to have a little bit more energy, sorry. So it's going to be a little bit higher wave number. And then an sp, so a triple bond, if this was a triple bond carbon hydrogen bond, then it's even higher at about 3,300. So that really will help. You'll see in a minute that it helps you identify things. And so just kind of summarize the different functional groups and where they tend to absorb. So our carbon-carbon single bond, our carbon double bond, and our carbon triple bond all have characteristic peaks. And then the carbon-hydrogen to those specific bonds. So if you have alkanes, and actually that's the least common functional group because most of the compound will be an alkane, and so it's going to be really hard to distinguish. So this is actually the least useful for alkanes. But what you'll usually find is that the CC stretch is around 800 to 1,300, and the CH stretch is just, like I said earlier, just below 3,000. Alkenes, which have the double bond, so the CC double bond tends to be at a higher region than the single bond, so 1,600, 1,680. And then the CH stretch, where the carbon is double bonded, will be just above 3,000. There's a couple other numbers here. We don't use those very often. A CC triple bond tends to be like I said earlier, around 2,200, somewhere in that range. And the CH stretch, where the carbon is triple bonded, is a little bit higher here than about 3,300. So here's some examples. So you can see here, usually you're going to see a big peak right in here at about 3,000 or just below 3,000. And that's for all the CH stretches that are not double bonded, so all the sp3 hybridized carbons. So you can see in this compound there's a lot of sp3 carbon hydrogen, so that's why you're seeing. So that peak is almost always going to be there. But this peak doesn't always show up. And so the fact that you have this peak right here at about 3,300 is this stretch right here between the C and the H, the C that's triple bond H. So that is an indication. There's not much else that is up here, although I said like an alcohol and an amine can be up here too. They tend to be just a little bit higher, and we'll see those in a minute. But this is this kind of indicates there's a CH where the C is triple bonded. And then this peak right here at around 2,200 is a real unusual to see anything here unless there's a triple bond. So this compound right here, if you put it through the instrument, will give you this spectrum. A lot of times you'll see some of this bending. So these are all the stretches, and then down here are the bending. These are a little bit, less useful, but sometimes they're helpful for identifying things, but you don't tend to look down here first. So we're looking in like in this region and then this region. So this is an example of an alkene. And again, now in most of this compound here, we've got a lot of carbon hydrogen, so most of them are sp3 hybridized. So you're going to see a lot of peaks right in here. These are the CH3, CH2 stretches, and that's not going to tell you much. But again, you kind of look for this 3,000 mark, and if you see something above 3,000, then that tends to be, like I said, like here, just above 3,000 is the CH stretch if the carbon is double bonded. The C double bond stretch tends to be right here around 1,300. There's not much else here. And then this is an example of an alkane. So you're not going to see anything above 3,000. So everything's right here around 28 to 3,000. Those are all the sp3 hybridized CH stretches. And then we're going to see CH bending and CC bending down in this region. Well, actually, this is the C8. This is the CC stretching and then the CH bending. All right, some other functional groups that would be very helpful to look for. Aromatic compounds. So remember that a benzene ring or compounds that have a benzene ring, see there's 3 double bonds, so they tend to be a little bit higher up than a single C double bond stretch, and so we tend to see a little bit higher up, around 1660 to 2000, we'll see some kind of a stretch that'll indicate the benzene ring. And then this is going to be similar. So if you've got a CH stretch where the carbon is double bonded, it's going to be just slightly above 3000. So let's look at an example of that. Here's an example. We tend to see the C double bond stretch here just above 3000. There's also a CH3 stretch, so that's that one over here. The C that stretches, but the stretches here for the aromatic hydrogens tend to be just above 3000. And then we tend to see a stretch right here around 1600 that indicates some kind of benzene ring, and then another one here around 1500. So these tend to show up. This is interesting. They didn't show it on the last slide, but we tend to see this little, we call this sometimes the fingerprint region or overtones, and we'll talk more about that in lab, but that is when you see this kind of pattern up here, that tends to tell you that you have an arene, so a benzene ring. Alcohols and amines give very distinctive absorptions on the spectrum. So the OH tends to be very broad and intense, meaning it comes down really far, and it tends to be up here. It's one of the highest on the wave number that we'll get, somewhere around 3400 to 3600, and we'll see on the next slide what it looks like. So it's broad and intense. The NH bond will be also in that region, but it tends to be sharper and less intense. So it looks more like this, whereas this one looks more like a tongue. And I've got some handouts on for the lab part where you're going to see kind of look for the differences. And actually, sometimes if it's an NH2, you might see kind of double fang, kind of a peaky thing like that. Well, let's look at the examples. So here's a typical alcohol. Big, like I said, sort of like a tongue. And when it says intense, it means it comes way down, almost to zero transmittance or 100% absorbance. And you can see here's the 3000 mark. So it's very high. It's up here around 3,500, and it's usually really wide. So that's the OH stretch. They're always going to have the CH stretches here. So again, that's nothing new. And then here we have some CH bending, but this is the key right here. And then to compare that with an amine, you can see it's in the same region, but it's not quite as broad or as deep. And it'll be more spiky, almost like fangs. If you have a primary NH, so like an NH2 group, you'll often see 2 peaks. Sometimes you'll just see one if it's like a NH where it's like a secondary amine, where if it's just one, then you'll probably be missing one of these. Kind of do that. And then again, we have our CH stretches, CH bends, CC bends, things like that. But here's the NH. That's really key. So again, we don't look at every single peak, but we're looking for specific ones. Another really, really important peak that you're going to be looking for is the C double bond O peak. So it tends to be, it's very consistent. It tends to be in this region, 1600 to 1780, 1650 to 18, somewhere in that region. It's going to move around a little bit, and so what you'll find is that it can actually be helpful in determining whether you have an aldehyde or a ketone or a carboxylic acid or something like that. And so again, there'll be more handouts with a little more specifics in lab, but this can be really helpful just to know that they're a little bit different. So you can see here an aldehyde versus here's an aldehyde with a double bond, so that changes that a little bit. Here's a aldehyde, but on a next to an arene, so it's going to be a little bit different. But you'll see on the next slide, I think, what it looks like. Nope, not on the next slide, on the next one. So ketones also have this same C double bond O stretch. You can see that they're slightly different numbers, but they're all in that same region. So there'll be a little bit to figure out exactly what it is. You'll be using other techniques, but it's really helpful to know this region. Somewhere around 1700 is the C double bond O rings. And then esters also have C double bond O stretches that tend to be a little bit different. So keep that in mind, that can be helpful. Here's some examples. So right here, you're going to see a big, strong absorption right here around 1700. So maybe just slightly, it could be anywhere in this region. And so you can see here, this is to pentanone, so 3-pentanone, where the ketone's on the 3rd carbon. So it's very symmetrical. And that's the C double bond O. You can see here, there's not much else. This is actually just a little bit of noise. There's not much here. And there's nothing really above 3000. And I'll tell you, as we're doing them, I'll kind of tell you if it's helpful to, if it's not something to keep track of, I'll kind of tell you to ignore it. So until you get more used to it. This is an example of carboxylic acid, and so normally if you've got ketones or aldehydes, they're going to tend to have that strong peak right here. This is interesting because you have both the ketone and the alcohol, and so you see sort of the tongue over here showing the alcohol. You see the C double bond O stretch over here, and then this actually makes it's kind of fatter. You can see compared to the last slide that this is fatter. It's not quite as sharp as the last one. And then you have this big sort of fat tongue here, and it kind of looks almost like a beard where it's shaggy throughout the whole thing. And that will often happen when you have hydrogen bonding. So that's partly why the OH stretch is so fat, because of hydrogen bonding. But you know, if you've got the O here, hydrogen bonding to a hydrogen, and then the HO over here on the next carbon, you know, kind of going like that, it's kind of holding them, so it's keeping the vibrations a little tighter than they would normally be, and so it's making that a little bit more jaggedy. Anyway, that's pretty much infrared spectroscopy. Again, we'll be talking a little bit about this more in lab, and I hope you enjoyed it. It's one of my favorite topics.